Here we'll give an introduction to quantum computation in geometric algebra. The contents are as follows. First, we'll introduce you to the concept of geometric algebra and some basic operations of it. Then we'll show you how to describe qubit systems in geometric algebra. Thirdly, we shall show how quantum gates are described. Lastly, we will show you the conclusions. So, what is geometric algebra, and why are we using it? In brief, geometric algebra gives complex and abstract algebraic structures their geometrical interpretations. First proposed by the English mathematician William Clifford in 1882, the importance of geometric algebra wasn't recognized until the American physicist David Hastings applied it to many fields. Geometric algebra provides us with insights in classical mechanics, relativity, the theory of quantum mechanics, and so much more. Hence, it is of no surprise that it can be utilized in the theory of quantum information and computation as well. Our goal here is to dig out the simplicity and intuition of mathematical operations inside quantum information and computation from a new perspective. Here we'll show you the fundamentals of geometric algebra. An algebra is a vector space closed under a certain multiplication. When we speak of the multiplication between vectors, one often thinks of the inner product and the cross product. The inner product, denoted as a dot, A dot B, is also called the dot product of the two vectors. But instead of the cross product, here we shall introduce you to a generalized wedge product between the two vectors, denoted as A wedge B. And here we'll introduce you to the geometric product of the two vectors, denoted simply as AB, which equals to the sum of the dot product and the wedge product. For those who are unaware or unfamiliar with the wedge product, it is basically a product that returns us with an oriented area. As shown on the bottom right is a parallelogram formed by the two vectors A and B. When we wedged more than one vectors together, for example, A wedge B wedge C, we obtained a trivector representing an oriented volume. The wedge product between n vectors returns us with a multidimensional object called the multivector. The geometric product between two parallel vectors, A and B, returns us with the sum of its inner product and their wedge product. The wedge product represents the area spanned by the two vectors. However, since they are co-directional, they are parallel, the area is simply 0, and we're left with the inner product. The inner product is commutative, hence AB equals BA. However, for the case for perpendicular vectors, A dot B equals 0, and we're left with the wedge product. When we switch the order of the product from A wedge B to B wedge A, we inverted the orientation. Hence, a negative sign must be included. Thus, we concluded that AB equals negative BA for perpendicular vectors A and B. For an n-dimensional Euclidean space Rn, it is endowed with an orthonormal basis, EI. We can take a subset of the orthonormal basis and wedge them together to obtain EI wedge EJ wedge dot dot wedge EK equals simply as E1 times EJ times dot dot times EK, where the product is the geometric product. These form the basis of the new space, a new vector space called Gn, or the geometric algebra for Rn. These multivectors are 1, EI, EIEJ, EIEJ EK, and so on. These multivectors that we generated are of different grades. 1 is of 0 grade. EI are grade 1 multivectors. EIEJ are grade 2. EIEJ EK are grade 3, and so on. These form the basis of the new geometric algebra, a vector space. The grade projection operator, denoted as an angled bracket sub r, picks out the rth grade element of the input. and by convention, we often write the 0th grade projection operator without the 0 at the bottom. Then, since we're introducing geometric algebra, it is without a doubt that we have to include their geometrical meanings. Two operations on multivectors are introduced: reflections and rotations. To reflect a vector A across the direction of a unit vector n, we will have that A reflected equals the vector A minus 2 times the parallel component of A to the vector n. And through computation shown on the screen, one can see that the reflected vector A equals to negative NaN. And as we all know, two consecutive reflections make up a rotation. As seen in the figure below, the vector A is first reflected along the unit vector m to obtain the vector B, on figure on the left. And then B is reflected along the unit vector n to obtain C, seen on the figure on the right. The total or rotated angle from A to C is theta, which equals to 2 phi, where phi is the angle between m and n. Therefore, we have the C equals to nm times A times mn via the equation of the reflection. Here we can denote the multivector mn by r, called a rotor that rotates a vector. And r tilde is the reversion of r. Next up, let us introduce the qubit system under the framework of geometric algebra. Instead of using the Euclidean basis to generate the geometric algebra, the geometric algebra we should use here are called the STA, the spacetime algebra, with 4 generators denoted as gamma naught, gamma 1, gamma 2, and gamma 3, where their inner products satisfy the following relation of gamma naught dot gamma naught equals 1, and gamma 1 or gamma 2 or gamma 3 dotted with themselves equals negative 1. We will use the even grade subalgebra of STA to describe quantum states. Moreover, we should introduce sigma 1, sigma 2, and sigma 3 defined as gamma I times gamma naught. The new basis of sigma i's construct a basis where we can generate a new algebra with grade 0 elements of 1, 3 grade 1 elements, 3 grade 2 elements, and 1 grade 3 element denoted as I, which we call the pseudo-scalar. It commutes with all multivectors in this space and owns the property of I squared equals to negative 1, just like the imaginary number. The basis we used is actually isomorphic to the Pauli matrices, hence the sigma notation. Sigma i's squared to 1, and capital I equals sigma 1 times sigma 2 times sigma 3. Moreover, the grade 2 elements satisfies the following relations. We can see that they are the same as the Pauli matrices if the capital I is the same as the lowercase unit imaginary I. Next up, the reversion operator reverses the order of multiplication of a multivector. The reversion of the basis negates only the grade 1 and grade 2 elements, leaving the grade 0 and grade 3 elements unchanged. In comparison to the reversion operator, the adjoint operator, when acted on a multivector, negates only the grade 2 and grade 3 elements. Finally, we can introduce a qubit. Proceeding on with the already developed notations by David Hastings and others, a single qubit state of ket psi can be represented as the following geometric algebra equivalence of psi equals a superscript 0 plus a superscript k plus I sigma subscript k, where the Einstein summation convention is used. We can also rewrite the geometric algebra form as psi equals 1 times a naught plus I sigma 3 a3 plus negative I sigma 2 times negative a2 plus I sigma 3 a1. We can see that the former part is just like this psi 1, and the latter part is similar to the psi 2 shown above. One can see that the unit imaginary number I has its geometric algebra equivalence of I sigma 3. The basis of psi 1 will be 1, and the basis of psi 2 will be negative I sigma 2. We can also see that the state psi is an element in the even grade subalgebra of G3, denoted as G3+. Moreover, we no longer need imaginary numbers in our formulation of quantum mechanics. Some basic examples are listed as below. The 0 state has its geometric algebra equivalence of 1. The 1 state has equivalence of negative I sigma 2. The plus state will be the superposition of 1 and negative I sigma 2. And the same applies to the minus state. The sets 1, I sigma 1, I sigma 2, and I sigma 3 are the conventional bases corresponding to a two-dimensional complex Hilbert space H2 with computational bases 0 and 1. Next up, we should introduce the Bloch sphere representation of a qubit. In the ordinary matrix representation, it is written as above, and we can hence deduce the geometric algebra version as below. Now, we can rewrite the latter part as a bivector, which squares to negative 1. Hence, psi is in fact a rotor, or in the case of quantum mechanics, a spinner. But if it's a rotor, then what does it rotate? In fact, the state psi, a spinner, rotates the sigma 3 axis to the Bloch vector representation of the state on the Bloch sphere. The Bloch vector denoted as S equals to psi sigma 3 psi tilde. Now that we know how to describe one qubit, let us try to describe an n-particle system. We can prepare n copies of the spacetime algebra, and hence we will have n copies of the same basis. The basis from different qubits commute under the geometric product, since it introduces two permutations and the negative ones cancel out. Therefore, all multivectors from different qubits commute, and we will be working in the algebra of ST plus tensor n. The even subalgebra of ST plus tensor n are of 4 to the power of n dimensions, but an n-particle state psi has a real dimension of only 2 to the power of n plus 1. Therefore, we need to introduce correlators to fix the issue of the redundant dimension stemmed from the multiplicity of the unit imaginaries. The details will not be presented here. Two correlators are introduced. An example for the two-qubit system is as shown below. For all spinor states, we can see that they are multiplied on the right by the state correlator D. This effectively replaces the tensor product normally used in quantum computing. We can also introduce the inner product between two n-particle states, psi and phi. It equals to a real part plus an imaginary part, same as that of the general complex matrix representation. Next up, let us introduce the density operator formulation in geometric algebra. A ket state psi has its geometric algebra equivalence written as follows, but we know that the sigma i's have its Pauli matrix equivalence. Hence, we can write down the SU2 isomorphism of the following. Written out, we find that it in fact equals to a 2 by 2 SU2 matrix, denoted as underlined capital psi. Given two qubits, psi and phi, the outer product is defined as following. We can see that it reduces to psi times E plus times phi tilde in the geometric algebra formulation, where E plus is 1 plus sigma 3 over 2. And in the case where phi equals psi, we have the density operator for a pure state, denoted as rho, equal to psi times E plus times psi tilde. density operators are especially useful when we're dealing with operators. Now, let us introduce the quantum gates in geometric algebra formulation. First are the single-qubit gates. Here we'll introduce the Pauli Gate, phase gate, and Hadamard Gate. As we have seen before, the Pauli matrices sigma I hat are isomorphic to the basis sigma I. So we have the following notation, where a ket state acted on by a Pauli matrix is equivalent to the sandwich product of the state by sigma 1 or sigma 2 or sigma 3 on the left and on the right by sigma 3. However, the multiplication rule is a bit too clumsy. Why do we want the sandwich product for a Springer state? Can we simplify it? Let us think of the geometric interpretation of the action on by the Pauli matrices. When a state is acted on by a Pauli matrix, it in fact rotates the Bloch vector by 180 degrees about the respective sigma j axis. When you speak of rotation in geometric algebra, one should immediately be reminded of rotors. Thus, we can write the sigma j operators as the rotor exponential negative I sigma j pi over 2, which reduces to negative I times sigma j. Hence, we know that sigma j hat has the geometric algebra equivalence of negative I sigma j. The two representations of the sandwich product and the negative I are only off by a global phase. And the multiplication by the unit imaginary is the same, where I psi in its geometric algebra equivalence is psi times I sigma 3. And as we see again, we don't need the unit imaginary I. In the Bloch vector representation, we can see that when a state is acted on by the phase gate of R alpha hat, it rotates the Bloch vector on the sigma 1 sigma 2 by vector plane by an angle of alpha. So we can see that the geometric algebra equivalence of the phase gate is in fact another spinner or a rotor, which equals to exponential negative sigma 1 sigma 2 times alpha over 2. Next up, the Hadamard Gate. We can write the Hadamard Gate as a sandwich product, as seen above. However, the multiplication rule can also be changed to the negative I version. And when we change to the operation on the density operators, we can see that it resembles the sandwich product on the matrix representation of transformation on density operators, where it transforms as negative IH times rho times negative IH dagger, where dagger is the conjugate operation we mentioned earlier. And furthermore, geometrically, we know that the sandwich product of the density operator is in fact a 180-degree rotation about the vector h. Lastly, multi-qubit gates. Here we shall introduce the swap gate, the control knot gate, Toffoli Gate, and the quantum Fourier transform. The swap gate swaps the superscripts of multi-vectors from the respective spacetime algebra. So we swap the j with the I and the I with the j. The control knot gate, in its matrix notation, can be decomposed as the sum of two tensor products. Its geometric algebra equivalence is written as below, where the x2 gate, conditioned on the first qubit, equals E1 plus E1 minus times sigma 2 1, where En plus or minus is defined on the right. We can see that E1 plus and E1 minus are actually conditioning operators. When E1 plus acts on the zero state, it returns the zero state. And when it acted on the 1 state, it returns 0, and vice versa for E1 minus. When they are applied onto the density operator rule, the rotation will be far simpler, as it is in fact, again, a sandwich product. Moreover, the conditional gates have a very clear and clean exponential form. For the conditional operator of the form, U2 conditioned on the qubit 1 equals to E1 plus E1 minus times U2, where U2 is a unitary gate on the second system conditioning on the first system, satisfying U2 squared equals 1. It can be rewritten in the exponential form of U2 conditioned on Y, a 1 equals exponential I times 1 minus U2 times E1 minus times pi over 2. And an example for the controlled NOT gate is written below. And for the case where E2 squared equals to -1, it can be rewritten in a simpler exponential form of U2 conditioned on 1 equals exponential U2 times E1 minus times pi over 2. And another example for the controlled NOT gate is given below. Lastly, we can combine the two theorems above to deduce the final theorem. If U2 has an exponential generator G2, such that U2 equals exponential G2, then the conditional operator can be rewritten in the exponential form of exponential G2 E1 minus. Similarly for the quantum Toffoli gate, where it takes in 3 qubits as input and only reverses the third qubit if the former two are 1s, else this third is left unchanged. We can express in geometric algebra of the Toffoli gate as x3 conditioned on 1, 2 equals 1 minus E1 minus E2 minus plus E1 minus E2 minus sigma 3, 1. Next up, the quantum Fourier transform. Let us define the Hadamard gate and phase gates of the rotation angle of 2 pi over 2 to the power of k for particle I as below. Now, starting from 2 qubits, we can observe that the QFT gate is represented as first multiplying the first qubit by the Hadamard gate, then multiplying it by the conditional phase gate, and then multiplying the second qubit by the Hadamard gate. Hence, its geometric algebra equivalence is as below. The same goes for the case of 3 qubits. For general n-qubit QFT gate, it is represented as an iterated conditional rotation. Finally, conclusions. Geometric algebra provides us with insights from another perspective and mathematical framework. It gives us a geometric interpretation to abstract algebraic objects. We introduced the geometric algebra formulation to quantum computation and gave geometric insights to quantum gates. Moreover, we also summed up all about the basics of GA quantum information computation and their notations. With geometric algebra, we will understand more about how quantum system works and look forward to the advance of the development of QIC in geometric algebra. Some things that we didn't discuss are the use of the norms of multivectors, denoted more often than not as the square root of the zero-grade projection of m times m tilde. So perhaps GA can provide us with new definitions of the distance measures with its geometrical meanings. Moreover, the unique algebraic structures in the wedge product and geometric product may provide us new ways in information encoding. Lastly, as of right now, geometric algebra has been widely utilized in control theory, signal processing, and computer graphics. So perhaps we can use the geometric algebra as a bridge between quantum theory and the respective fields, for example, quantum control theory, and discover more about the theories. And that's all for our discussions. Here are some of the references.